In the previous lecture, we finished unit step function and also Heaviside function. We now have Laplace transform of Dirac-Delta function. The Laplace transform of Dirac-Delta function. Definition of Dirac-Delta function. We say the Dirac-Delta function delta of t minus a is defined by, this is Dirac-Delta function. It's called Dirac-Delta function. It's defined by, it equals to infinity if t equals a. If t equals a, then the Dirac-Delta function is infinity at t equals a. And it's zero otherwise. That means for any other value of t except a, it equals to zero. And here we say the integration of Dirac-Delta function from 0 to infinity, it equals 1. And the integration of f of t multiplying by Dirac-Delta function from 0 to infinity, it equals to f of a. It is f of a. For example, if we have, let's say, from 0 to infinity, let's say sine t, Dirac-Delta function of t minus, let's say, 2 dt. This equals f of a. What's a here? A is this value. A equals 2. Okay. Comparing with this one, a is 2. That means it's f of 2. So what's f of t here? F of t is this one. This is f of t. F of t is sine t. How about f of 2? F of 2 is sine 2. That means the result of this integration equals sine 2. Now we have Laplace transform of Dirac-Delta function. The Laplace transform of Dirac-Delta function. We say the Laplace transform of delta of t, here a is 0. Here a is 0. We have the Laplace transform of Dirac-Delta function of t minus a. A here is 0. If it is 0, so you just get 10. Sorry, t. So the Laplace transform of Dirac-Delta function when a is 0, it equals 1. It is 1. And here we have the Laplace transform of Dirac-Delta function t minus a. It equals e to the power minus as. That's e to the power minus as. Let's take an example here. We say the Laplace transform of let's say Dirac-Delta function of t minus 3. This equals e to the power, here just determine a. What's a here? What's a? A is this number. A is 3. That's e to the power minus as. We just replace a by its value, which is 3. Let's take another example. The Laplace transform of a Dirac-Delta function. Dirac-Delta function of t plus 4. How about this one? What's a here? A is minus 4. A is minus 4 because he is positive. So a is minus 4. That's why it becomes positive. It equals to e to the power minus, sorry, it's minus 4. That's it. It's minus 4. E to the power minus as. What's a here? A is minus 4. Minus 4. And it becomes 4. So it is 4s. This is the Laplace transform of that Dirac-Delta function. And the third one, here, we say the Laplace transform of f of t multiplied by Dirac-Delta function of t minus a. F of t multiplied by Dirac-Delta function of t minus a equals e to the power minus as times f of a. Here we should first determine what's f of t and what is a. Then we just replace them here. We just substitute there. Let's take an example. Let's example for that part. If you take an example here, we say the Laplace transform of Dirac delta function. The Laplace on, let's say, sine 2t Dirac delta function of t minus, let's say, 4. What's this Laplace transform? We say it equals, let's first identify f of t and a. Here, f of t, this is f of t. F of t is sine 2t, and a is 4. We say it equals to e to the power. We just apply this rule. We just apply this rule. It's e to the power minus as, e to the power minus as times f of a. That means in f of t, we replace t by a. We have a is 4. We just replace a in f of t and in e to the power minus as. This equals to a here is 4. It's minus 4s. What's f of a? This is f of t. F of t is sine 2t. How about f of a? F of 4. F of 4. It is sine 2 times 4. We just replace t by 4, which is sine 8. Okay. So f of a is sine 8. Is it? Let's take another example. The Laplace transform of, let's say, t squared Laplace, sorry, Dirac delta function of t minus, let's say, pi. This equals to what? It equals to e to the power minus as. A here is pi, so it is e to the power minus pi s times f of a, which is f of t is t squared. We just replace t by pi, which is a. It's pi squared. This is the result. This is the Laplace transform for this function. The proof of these proofs are not required from you, but you can do it by yourselves. Okay, you can do it by yourselves. Proof of these rules. We now have some examples about the above rules. It says find the Laplace transform of f of t. If f of t to be e to the power minus 2t times the Dirac delta function of t minus 2. T minus 2. We say the Laplace transform of e to the power minus 2t plus Dirac delta function of t minus 2. It equals to the Laplace transform of each one separate, because it's the sum of two functions. So it's the Laplace transform of e to the power minus 2t plus the Laplace transform of Dirac delta function of t minus 2. Here we say the Laplace transform of e to the power minus 2t, it equals 1 over s minus a. Let's see, let me open the game here. Let's return to the beginning of the chapter. We have these rules. We say e to the power at. E to the power at, its Laplace transform is the Laplace transform here for this function is 1 over s minus a. So we should identify a. What's a here? That means here the Laplace transform for this part is, let me write down below, it equals 1 over s minus a. What's a? minus 2. This equals to 1, sorry, plus. And the Laplace transform of Dirac delta function of t minus 2. What's the Laplace transform of Dirac delta function of t minus a? This is the Laplace transform of t minus a equals to e to the power minus as. It equals e to the power minus as. Here, a is 2 plus e to the power minus 2s. And this equals to 1 over s plus 2 plus e to the power minus 2s. This is the Laplace transform for f of t. Okay? It's only applying the rules. It's so easy. If you just know the rules, it's easy. And you have, sorry. No. All I be okay. Here we have the Laplace transform of t cubed delta of t minus pi over 2. We have f of t, which is multiplied by a Dirac delta function. So you apply this rule, the third one. You apply the third rule, because here we have f of t, which is multiplied by Dirac delta function. The Laplace transform of a function which is multiplied by a Dirac delta function is e to the power minus as. We should first identify f of t and a. We just replace a here and here. That's all. For this one, we say the Laplace transform of t cubed, the Dirac delta function of t minus pi over 2, f of t, first identify, determine those, I mean f of t and a. F of t is t cubed, and a is late. A is pi over 2. Okay? Here, f of t is t cubed, and a is pi over 2. How about f of a? We need f of a also. F of a is pi over 2 cubed. We say that the Laplace transform of a function which is multiplied by the Dirac delta function is e to the power minus as times f of a. We found f of a before, and also we replace a here. It equals to e to the power minus pi over 2 s times f of a is, this is, sorry, let me write down again. F of a is f of pi over 2, which is pi over 2 cubed. It is pi over 2 cubed. That's the Laplace transform for that function. We have another example. Find the Laplace transform of sine 2t times delta Dirac delta function of t minus 2. What's f of t and what is a here? F of t is sine 2t, and a is 2. So from this, f of 2, which f of a, which is f of 2, equals to sine 2 times 2. Because here you have this 2 and you replace t by 2. We get sine 4. This is f of a, which is f of 2. Now we say the Dirac delta function, so the Laplace transform of a function f of t, which is multiplied by a Dirac delta function, is e to the power minus as multiplying by f of a. We found both a and f of a. We just replace them here. It equals e to the power minus 2s, because a is 2, so you get e to the power minus 2s. F of a is sine 4. That's it. It's easy. It's about امتحان شهر واحد امتحان ولا قرصني أسانا لم شابتر بس يا ساكن بزاني تريد ياسر ها شيء اتهاي شيء ونعرف الديفينيشن بوك على شو يعني يكسر أنجام نسي نعم ستيفاني بوكيت شنو دسكو أسانا هيزني يكسر أو مش أنجام ستة okay. We now have another section which is about inverse Laplace transforms. Look, we say the Laplace transform of sine 2t times Dirac delta function of t minus 2 equals e to the power minus 2s sine 4. How about the Laplace inverse of e to the power minus 2s sine 4? We say this equals to sine 2t Dirac delta function of t minus 2. We return the function of f of s to f of t. Okay, we say the Laplace transform of, let's say, we say the Laplace transform of t squared. We say the Laplace transform of t squared equals 2 factorial, which is 2, dividing by s to the power 3, s to the power n plus 1. Let's see here, that's the rule. That's n factorial dividing by n to the power s plus 1. Sorry, s to the power n plus 1. لا في سناك اسن من اللي احنا نسبت بزان لابلاس انفيرس شيء عمي او بزان اسن من اللي احنا. Here we say the Laplace inverse of 2 over s cubed equals to t to the power 2. And we say, let me clean this. The Laplace of, let's say, cosine. The Laplace of cosine, let's say 3t, it equals s dividing by s squared plus a squared. A here is 3, is it? It's s squared plus a squared, which is 9. These are the rules. Look, for cosine, it's s over s squared plus a squared. And then we say the Laplace inverse, if you have given this function, to find the Laplace inverse of it, we say the Laplace inverse of s over s squared plus 9, it equals to, it's easier to write down it like f inverse of s over s squared plus 3 squared to find a. A here is 3. It is cosine 3t. We say the Laplace inverse of s over s squared plus 9 is cosine 3t. Yes. Which one? This one, we say if you have f of t, which is multiplied by Dirac delta function of t minus a. The Laplace transform for this function is e to the power minus as times f of a. What's a here? A is this one. Okay, that's it. Sorry. Ba نخشى بوتي sine cosine exponential هالشيء. Vale. هالش نخشى بك إتد كشمان. Polynomial هالشيء بكشني. Okay. We applied this rule for the above example, but here I'm talking about inverse Laplace. And so, what about if we have, sorry, no, tangents and cotangents? We have another. So how about this one? If you have the Laplace of, e to the power, let's say 3t times sine t. How about this one? Here, this is a. We use the properties. Look, we have some properties of these. Let me check. That's it. We say if you have the Laplace transform of e to the power it, which is multiplied by a function of t, it equals to f of s minus a. Here, we are going to find the Laplace transform for the function f of t, and then replace each s by s minus a. For example, if we have the Laplace transform of, let's say, e to the power 2t times, let's say, sine t, the same which I have written down there. This is f of t. We find the Laplace transform for sine. The Laplace transform for sine is a, here it's 1 over s squared plus 1 squared, which is 1. This is the Laplace transform for sine t. Then we replace each s, this f of s. We replace, we say we are going to find f of s minus a. A here is 2. This equals to 1 over s minus 2 squared plus 1. Okay, we talked about these examples before. Oh, it's in the other file. Here we say the Laplace transform of e to the power 3t. Let me change this to, let's say, 2t. Okay, e to the power 3t. We say the Laplace transform of an exponential function which is multiplied by f of t. You see the Laplace transform of e to the power at times f of t. What we do, we are going to find the Laplace transform for f of t, which is f of s. Then we replace each s by s minus a, which is equals to s minus a. We are going to find first the Laplace transform for this function, and then we replace each s by s minus a. And here we have a similar function. It is e to the power 3t times sine 2t. This is f of t. We say f of t equals sine 2t. What's the Laplace transform of f of t? It equals to what? Equals to a, which is 2, dividing by s squared plus a squared, which is 4. Then this is f of s. How about f of s minus 3? Minus 3. Yeah, minus. It's minus. Multiplication. That's it. It's f of s minus s. Yeah. We say f of s minus 3 equals 2 over s minus 3 squared plus 4. Okay, that means this Laplace transform equals 2 over s minus 3 squared plus 4. Okay, how about the Laplace transform for this function, of s? It is e to the power 3t sine 2t. Okay, we say the Laplace transform inverse of 2 over s minus 3 squared plus 4, that equals to, as you see here, we have f of s minus 3. That means we must have e to the power 3t. Okay, because we have f of s minus 3. Since we replaced s by s minus 3, that means we must have e to the power minus 3t. So what's the other function? What's f of t? F of t here, f of s equals 2 over s minus 4, s squared minus 4. So plus 4. This is similar to sine function. This is similar to sine function, the Laplace of sine function. This equals to 2 over s squared plus 2 squared. Here a is 2. And you have 2 here also. This equals to, and so the Laplace inverse of this is sine 2t. That means it equals to sine 2t. So the Laplace inverse for 2 over s minus 3 squared plus 4 equals e to the power 3t sine 2t. This is about finding the Laplace inverse. We now try to solve some examples. Okay. We say the Laplace inverse of f of s is f of t. We return to the original function. Return the result f of s to the original function, to f of t. We say the Laplace of f of t is f of s. And the Laplace inverse of f of s is f of t. We return to the original function. We have some properties of Laplace inverse. We say the Laplace inverse of f of s minus a, it equals e to the power at times f of t. It's e to the power at times f of t, because here we have f of s minus a. That means we must have exponential function which is multiplied by f of t. And the Laplace transform of e to the power minus as over s, it is the unit step function h of t minus a. We talked about this before. We said the Laplace transform of h of t minus a is e to the power minus as over s. And the Laplace inverse of e to the power minus as f of s equals to f of t minus a times h of t minus a. This Heaviside function or unit step function. Then Laplace inverse of e to the power minus as is Dirac delta function of t minus. That means if we have e to the power minus as, then its Laplace transform, its Laplace inverse is the Dirac delta function of t minus. The Laplace inverse of e to the power minus as times f of a, it is f of t times Dirac delta function of t minus a. Okay. So if you have these functions, we can directly write down their results like this. Okay. We talked about these all, I mean the right hand side ones, and we found their Laplace transforms. The Laplace transforms are these. These rules we studied before. It's for Laplace transform. For inverse, we return. So here we have a Laplace inverse of 1. What's the Laplace inverse of 1? These are the rules. It's not belong to these rules. It's not belong to these rules. It's not belong to these rules. Look, we just studied that, today studied that the Laplace transform of Dirac delta function is 1. The Laplace transform of Dirac delta function of t minus 0, or where a is 0, is 1. How about the Laplace inverse of 1? It is Dirac delta function of t. That's it. We say the Laplace transform of Dirac delta function is 1, and the Laplace inverse of 1 is the Dirac delta function. Yes, yes. Okay. So this trivial example, we say it equals to Dirac delta function of t. Okay. That's Dirac delta function of t. And then we have some more examples. It says find the inverse Laplace transform for the following. For the first one, we have capital F of S equals 4 over S squared plus 9. This is similar to sine. This is similar to Laplace of sine function. Okay. Sine of what? 3t. Okay. So the result is sine 3t. Look, for sine, we say the Laplace transform of sine at equals a over a squared plus a squared. So we must have a in the numerator also. Here, this is 4. This is 4. So we must have 3 there. We multiply it by 3 and divide by 3. And we take that 4 out of the Laplace inverse. Okay? We say, let's solve the first one. The Laplace inverse of 4 over s squared plus 9. This equals to Laplace inverse of 4 times 3, 1/30. Okay, we multiply by 3 and divide by 3, and we can take this 4 out of the Laplace inverse. So you have 4. That's it. But let me do it in 2 steps. One of dividing by s squared plus 3 squared, and this equals to, we take this 4 out of the Laplace inverse. We get 4 over 3 times the Laplace inverse of 3 dividing by s squared plus 3 squared. This is the Laplace of sine 3t. So the Laplace inverse for 3 over s squared plus 3 squared is sine 3t. We return it. We say the Laplace of sine 3t equals 3 over s squared plus 9. And here we have this. So the Laplace inverse for this function is sine 3t. That means it equals to, yes, you write down 4 over 3. The Laplace inverse for this part is sine 3t. So that's the result. It's easy. It's only applying the rules, nothing else. The second one, we have 1 over s to the power 5. We have 1 over s. Since in the denominator you have only s without plus or minus anything else, that means it's polynomial. It's t to the power something. What's the power of t there? We say the Laplace, let's first write down the function. We say the Laplace inverse, it's the first one, the second one. The Laplace inverse of 1 over t to the power 5, sorry, s to the power 5. We say the Laplace transform, it's the rules here. See the Laplace transform of t to the power n. It equals to n factorial, we must have n factorial in the numerator, dividing by s to the power, dividing by s to the power n plus 1. It is 4 factorial. 4 factorial dividing, we must have 4 factorial divided by s to the power 5. So it's t to the power 4 because it's added by 1. Second, later I get to n bit, to an jere chane in zaid yaka. Later to an piers one. Got it to an chane چوارە بەڵام ئەوێت چیشمان هەبێت ئەوێت چوار فاکتۆریەڵشمان هەبێت لەسەر یەکە. Okay, so let's do it. Here we say, sorry, yes, we multiply it by 4 factorial and divide it by 4 factorial. Okay, we say it equals to the Laplace inverse of 4 factorial divided by s to the power 5. Why don't you multiply it by 5 factorial? Because we have t to the power. This is n plus 1. We must have n factorial. Okay, we must have n factorial. This n plus 1 is 5. So how about n? N is 4. 4 factorial dividing by s to the power 5. And here we divide by 4 factorial. This equals to, we apply this rule here. If we have this, we now have this one. So if we take its Laplace inverse, it becomes t to the power n. N here is 4. Okay, and here is 4. This equals to 1 over 24 t to the power 4. Is it? This is n. This is n plus 1. We say if you have n factorial over s to the power n plus 1, its Laplace inverse is t to the power n. T to the power n, n is 4. So it is t to the power 4. This is the result.
Sorry, why did we multiply by 1 over 4?
Factorial. Because we multiplied by 1 over 4 factorial, so we must divide by 1 over 4 factorial. Why? Why do you need to multiply and divide by that number? Because we say the Laplace inverse of, sorry, the Laplace of t to the power n equals n factorial dividing by s to the power n plus 1. In the denominator, you have s to the power 5. That means n is 4. So you must have n factorial above. Then we can take its Laplace inverse. A bit factorially in ناقصك من هبل السنة. إن جاتوا Laplace inverse ودي. شو أكره سكر دو كره ديك سنة. N factorial is n times n minus 1 times n minus 2 up to 1. So 4 factorial is 4 times 3 times 2 times 1. That's 24. That's why it's. And here, since you must have n factorial above, so you must have 5 minus 1, which is 4 factorial above. We multiply it by 4 factorial and dividing it by 4 factorial. It's similar to the above one. Here, as I said, we must have 3 in the numerator. And here, we must have 4 factorial in the numerator. Okay, that's why we multiply by 4 factorial and divide it by 4 factorial. And get 1 over 24 t to the power 4. This is the result. The third one, f of s is 6 divided by s minus 1 to the power 4. The Laplace inverse of 6 divided by s minus 1 to the power 4. Since all the denominator is raised to an exponent, this f of s minus 1, is it? We have f of s minus 1. That means we must have e to the power 1t was multiplied by f of t. We now need to find f of t. We need to find f of t. If we have capital F of s minus a, so we must have e to the power, the Laplace inverse of this. We must have e to the power at times f of t. Okay, here a is 1. That means we must have e to the power 1t. And now we are looking for finding f of t. How? This is f of s minus a, which is 1 of 6 over s minus 1 squared to the power 4. So f of s minus 1 equals 6 over s minus 1 to the power 4. How about f of s? 6 over s to the power 4. Is it? It's similar to the above one. This is polynomial, it's t to the power something. What's the power of t? Here, it's n plus 1. So n is 3. And n factorial is 3 factorial with 6. And it's 3 times 2 times 1. It's 6. We have 6 in the above. So you don't need to multiply by a number and divide it by a number. Because you already have n factorial in the above. So the Laplace inverse of this one equals to what? Equals to t to the power 3. That's t to the, why? Because we said the Laplace of t to the power 3 is 3 factorial dividing by s to the power 3 plus 1 is 4. So the Laplace inverse for this one is t to the power 3. So the result here is let me do it in another step. So the Laplace inverse of f of s is the Laplace inverse of 6 over s squared, s to the power 4. That equals to t cubed. So the result here equals e to the power 1t times f of t here is t to the power 3. That's all. If we take the Laplace for this result, we must get the above one. Let's do it. We apply this rule. That's it. We apply this rule here. We apply this rule. We say if we have e to the power 80 multiplied by f of t, it's f of s minus a. That means here we are going to find the Laplace transform for f of t, and then we replace each t by a, each s by s minus a. The Laplace of e to the power t times t cubed is the Laplace of t to the power 3 is 3 factorial to s to the power 4. Okay, and here you have e to the power t. We replace each s by s minus 1. That's all. That's 6 over s minus 1 to the power 4, which is that one. And just to satisfy, this is about this example. So let's take a break. Yes, let's take a break for 10 minutes. We now have 2 examples about finding the Laplace inverse. We have given 2 functions of s, and we should find the Laplace inverse for those 2 functions. For the first one, is 2 over s minus 2 squared plus 9. Since you have s of f of s minus 2, since it's s minus 2 squared, that means it's f of s minus 2. So you must have e to the power 2t in the result. Okay? We say the Laplace inverse of f of s minus a equals to e to the power 80 times f of t. Since here we have s minus 2 squared, that means it's f of s minus 2. Okay? Let's solve it. We say this Laplace inverse is it's Laplace inverse of f of for a for part a f of s minus 2. Is it? It is the Laplace inverse. It's e to the power 2t times e to the power 2t times the Laplace inverse of f of t. What's f of t here? What's f of t here? F of t is, look, first let's find the Laplace inverse of 2 over s squared plus 9. We have this one. We are going to find the Laplace inverse for this function. Okay, this f of s. F of s minus 2 becomes e to the power at times Laplace inverse of f of s. What's a here? A is 3. A is this one. Not, we don't look at the above one. Look at the denominator. It's s squared plus a squared. So in the denominator we have 9. 9 is 3 squared, which is 3. This equals to e to the power 2t Laplace inverse of 2 over s squared plus 3 squared. A is 3. So you must have 3 in the above. It's similar to sine function. It's similar to the Laplace of sine function. Okay. We say the Laplace of sine function, sine at, equals a over s squared plus a squared. We have s squared, you have a squared, but we have no a in the numerator. So we must have a there. How do we get a there? How do we get 3 in the numerator? We multiply and divide by 3. This equals to e to the power 2t times 2 over 3. We take this 2 out and multiply by 3 and divide by 3 to get 3 in the above. Laplace inverse of 3 over s squared plus 3 squared. This equals to what? This is the Laplace of sine 3t. So the Laplace inverse for this function is sine 3t. Is it? It is 2/3 e to the power 2t times sine 3t. This is the result. Okay. The second one is for yourself. It's easy. Just take 2 as the common here. And a here is this, the square root of 5 over 2. A here is square root of 5 over 2. You must have above, and you need to multiply by square root of 5 over 2 and divide by that. Then you get it. So it's actually not that. This is a polynomial function actually. It's polynomial. Here we take 2 first, and then we get s plus 5 over 2. Here a is minus 5 over 2. A is minus 5 over 2. So it's f of s minus a. Let's do it for b. We say the Laplace inverse of 3 over 2s plus 5 to the power 3. First, we must have s alone without coefficients. That means we must take it as the common. If we take 2 between these two terms, what we get? We get the Laplace inverse of 3 over 2 cubed s plus 5 over 2 cubed. We get that. Is it? We just took 2 as the common between these two. It's in the bracket, so we must give the exponent to it also. It equals to 2 cubed is 8. So you get 3 over 8. Laplace inverse of 1 over s minus 5 over 2 to the power 3. This is f of s plus a. So s minus a. We have f of s minus a equals 1 over s plus 5 over 2 to the power 3. How about f of s? F of s is 1 over s cubed. Is it? And also we have a. A here is minus 5 over 2. Okay, so the Laplace inverse of this, it equals to e to the power a here is minus 5 over 2 because it's plus. It's minus 5 over 2t times Laplace inverse of 1 over s cubed. We must have this n is 3. We must have n minus this n plus 1. N plus 1 is 3. How about n? N is 2. So we must have n factor above. We multiply it by 2 and divide it by 2. You get the result. This for yourselves, okay? It's only the idea for solving it. Try to finish it by yourselves. It's easy. So the result will be 3. The result is 3 over 16 e to the power minus 5 over 2t t squared. This is the result. Do it by yourselves, okay? We now have finding inverse Laplace transforms using partial fractions. Have you studied partial fractions before?
Yes, indeed.
Yeah, in integration. Okay. Here we say there are a few types of denominator that you should know. A linear factor, s plus a. It gives a partial fraction a over s plus a. Okay, so it equals, if the denominator is s plus a, we say it is a over s plus a, where a is a constant to be determined. Here, to repeat factors, we say s plus a squared. If this is the denominator, we say it equals to a over s plus a plus b over s plus a squared. And if this cubed, that's a over s plus a plus b over s plus a squared plus c over s plus a cubed. And if this to the power 4, we go up to power 4 for the denominator. And then for quadratic factor, we say if the denominator is this one, it's quadratic. We say it equals to p times, let's say as plus b. P and q are constants in the numerator. It says ps plus q, or you can say as plus b over the denominator, s squared plus ps plus q. Okay, and if it's repeated, we are going to write down this. Agar hatu 20 gorawa kanaka wanaka do أو كاتالين كونستانت صار بي اس زائد كونستانت بلام أجر هاتو جوراوك تواني لسه نبو بوي تواني كسر كوانا كب ياخد كوانا كش تواني لسه نبو أو كاتالين كونستانت لسه شيرك بلام أجر هاتو كوانا كت تواني بون بينج بيت أو كاتالين شيء كاتا كونستانت لسه كوانا كب تواني زائد كونستانت لسه كوانا كب تواني زائد كونستانت لسه كوانا بتواني سه بمشيوه بردام هتا بينج. Okay, here you have an example about finding the partial fractions of this function. Here we have this 3s plus 1 divided by s squared minus s minus 6. Here we cannot find the Laplace inverse for this function directly. There is no similar functions which have the Laplace of this form. So in this case, we must use partial fractions. After using the partial fraction, we get this one. And it's similar to exponential functions. This is similar to exponential functions, Laplace transforms. So now we are trying to find the Laplace, find the partial fractions for this function. We say we first need to factorize the denominator if you could. If you couldn't, it's okay. You don't need to do it. Here, we should first factorize the denominator. Denominator is s squared plus s minus 6. We can factorize it. It's s plus 2, s minus 3. That's factorization of the denominator. Now, since you have two brackets in the denominator, we say a over first bracket plus b over the second bracket. It's like this. We say it equals to a over the first bracket plus b over the second bracket. Why do we write down only a? We don't write down as plus b. Because it's linear. The power of s here is 1, and the power of s here is 1 also. That's why we say a over the first bracket plus b over the second bracket. So what if you have, let's say, if you have a squared plus 2s minus 8 dividing by a squared plus 1 s minus 2. This equals to what? Equals to as plus b dividing by a squared plus 1. Because this is, here we have a squared. That's why we must write down as plus b. Therefore, the second one, for the second, we don't need to write down that. Why? Because it's linear, plus c over s minus 2. So how about this one? If you have minus here, s squared minus 1. Here we can't factorize it. We can't factorize it. So you must factorize to the simplest form. It equals to s squared plus 2s minus 8 dividing by s minus 1, s plus 1, s minus 2. And this equals to a over s minus 1 plus b over s plus 1 plus c over s minus 2. We do that. This is the partial fraction of that fraction. We now try to solve the above example. We say the factorization of the denominator is s plus 2s minus 3. It is a over s plus 2 plus b over s minus 3. Now we multiply this by that one and this by that one. Okay, we get a times s minus 3 plus b times s plus 2. And we equal it to the numerator. We equal it to the numerator here, which is 3s plus 1. Let's see. We have 3s plus 1 dividing by s squared minus, let's say, s plus 2, s minus 3 equals to a times s minus 3 plus b times s plus 2. All divided by s plus 2, s minus 3. These two denominators are equal, so their numerators must be equal. Because these two fractions are equal. If the denominators are equal, so their numerators must equal also. That means here we say a times s minus 3 plus b times s minus 2 equals 3s plus 1. We equal these two, then we find the values of a and b. After finding the values of a and b, we return them to here and here. So a here is 1 and b here is 2. We get these two fractions. It's easy to find the Laplace inverse for each of these. Each of them is an exponential function. It's exponential of minus 2t plus 2 times exponential of 3t. That's enough for today. So we will try to finish tomorrow. Okay, let me clean it first. We'll try to finish this tomorrow. And it's important. And here I'm going to show you last year test 2. Yes, I'm going to prepare the questions.